So let's go a bit deeper with this, with the matrix analysis. I want to connect this to differential equations in particular. So again, this makes more general and a little more abstract the connection that's been running through all these videos, which is taking this sequence of integers and not worrying too much about the number theory part of it, but looking at how it works as a function and what properties it has as a function. So taking an analysis or calculus point of view. So the idea is that everything is an exponential. It's really the idea of an exponential function is actually incredibly deep. It shows up very many places in mathematics that you wouldn't expect. And so we're going to connect this to exponentials and differential equations and the flow of solutions of differential equations in continuous time. So here's what we had. Let's look at the general case, the totally general Lucas sequence case. We had this matrix A, and then we diagonalized it, and we get the eigenvalues alpha and beta, which really determine analytically what's going on with the solutions of these. What do they look like as functions? So one thing you can do is you take the logarithm of a matrix, which if you've never done that, it's really cool. You can take the exponential of a matrix, and we'll do that in a second. You can take the logarithm. Once you've diagonalized a matrix, everything is easy, basically. You just do whatever you want to do to the diagonals. Now, that said, in the case where we are interested in, when you look at, for example, twisted Fibonacci and Lucas, un and vn, sort of the stars of this whole series, the eigenvalues for that are I phi and I psi. And we put those i's in for a reason, to make things nice and connect with sines and cosines. But it does mean we're taking the logarithm of complex numbers, which we've seen already in previous videos. So you do have to choose what's called a branch of the complex logarithm function. That needs some care. It can get you in trouble. But again, that goes a little more in the direction of complex analysis than I really want to go for. I've studiously avoided trying to worry about that, and I think I've managed just not to say anything that's actually incorrect. Okay, so that allows us to think of what's going on here as the solution of a differential equation, or in other words, a continuously varying flow. So here's what we do. You just, for any real t, we can define a to the tth power. Another really cool thing to do. Take a matrix to a real number power. So a 2 by 2 square matrix to the pith power. It makes sense. As usual, what you do is you use an exponential to define that. You define it as e to the t ln a. The ln has already been defined up here. And the matrix exponential, same deal. You just conjugate it with the p and the p inverse and do the exponential in here. Okay, so what does that amount to? It really just amounts to doing what you think you should do. If you always have this mantra of diagonal matrices are easy, and diagonalize your matrix and do what you think you should do on the diagonals, and then relate it back to your original matrix with your change of basis matrices, p and p inverse, that's how you take the tth power of a diagonalizable matrix. So so I could have just said this equals this, but I really do want to emphasize the idea that everything's coming from exponentials. And that's because it relates to differential equations. This is how you solve linear systems of differential equations in a somewhat fancy way. Again, if this is totally brand new to you, it's probably going to be a little mysterious because I didn't decide to sort of teach a whole course on this right now. You've got a differential equation, a prime of t is some fixed matrix times a of t, and you start with the most natural starting point in the world, besides 0, which would be stupid, you'd just get 0, is the identity matrix. And what's B? What's the matrix that encodes the evolution of the differential equation? It's ln A. So the way you solve this kind of differential equation is you take e to the t times b. Okay, so that's another way to write that. If you want to be a little more concrete than that, you might have seen this kind of way of solving differential equations. You might not have gotten quite to this level of generality. If you just have a vector ODE, and so let me draw a picture of that. You've got the plane. We're in 2 dimensions. You can do all this in n dimensions as well, but we start out with 2 term recurrences, so it's all in 2 dimensions. So here's the x-axis, here's the y-axis. We start out. This was focused. yesterday. We start out with some, here we go, okay, some vector v naught, and then there's some rule which is expressed by a direction field that takes us on a journey away from that, okay, and that's going to be v of t, okay. Well, when that rule is a linear rule, when the arrows are determined by just taking the position you're at and multiplying them by a linear matrix, then you get a very simple solution, which is given by these matrices. Okay, so the simplest case is, let's say you start out at 1, 0. 1, 0. That's my v naught. Then it's going to go off in some direction. And that's just given by the first column of this matrix. It's just going to be the first column of A of t. So you take this guy and you just say what the first column is. In general, the story is that if I'm going to solve this vector linear differential equation with a given starting point, you take B, this matrix, you multiply it by however much time you're going to go, you exponentiate it, which involves diagonalization, and multiply by v naught. Okay, so again, I hope that's review, because otherwise it's going to be, I think, kind of mysterious. So the point is that if you're thinking of everything in terms of differential equations, smooth dynamical systems, flows of, you have sort of a field, you can think of it as like a velocity field of a fluid, and you're looking at all these different initial conditions and where are they going to go, how are they going to flow, then the key is the matrix B. So I want to analogize this to some much more familiar and better behaved matrices B. Okay, so for example, the simplest case is where B is actually diagonal to start with. And you don't have to diagonalize it, it's diagonal. If B is just some number here, let's just say they're real numbers to be nice and simple, some real number here, some real number here, then the exponential e to the tb is really easy. You just do what you should do to the diagonals. Okay, so just treat them as numbers. Okay, and the vector solutions are really easy. You just multiply this times a mate times a vector. Let's see, I should probably write it. You're just going to take this and you're going to multiply it by whatever your starting v naught is. Maybe it has x coordinate x naught, y coordinate y naught. And it's a very simple thing. You're just going to scale the original x input by an exponential function and scale the y input by a certain function. So there's not a lot of interesting geometry or algebra going on there, I would claim, but that's kind of a basic example. More interesting is, let's take a matrix that is diagonalizable, has simple eigenvalues, but is not diagonal, and see what that does. Okay, so I'm going to go through this real quick, and it's really kind of a pause and do this exercise, review of the differential equations. Again, a little bit more eigenvalues and eigenvectors. If you want to exponentiate, you have to diagonalize it. The eigenvalues of this are easy to find. They're 1 and minus 1. The eigenvectors are 1, 1, and 1 minus 1. Oop, just kidding. And if you put that into a matrix, that's P. Invert it, it's easy. And if you multiply P times e to the t to the minus t, which is the exponential of the diagonal version, times P inverse, you get Cauchys and Synges. Okay, a very, very classic example. And what's really pretty about this, and I'm going to use a nice little app here, so I can get a better picture than I can do by hand. What I'm putting in here is exactly the direction field for this system of differential equations. This, for example, let's convince ourselves that's true. So this is the matrix, again, that switches rows and columns. So if my x coordinate, my x position is large and my y position is 0, then the vector has a large y coordinate, y component, and 0 x component. If the x coordinate is 0 and the y coordinate is large and positive, the x component of the vector, the flow vector that's pushing me around there, is large and positive, and the y component is 0. Along this line, if x and y coordinates are equal and positive, x and y components of the arrows are equal and positive. Similarly here, but they're negative. Here, if they're opposite, if the x and y coordinates are opposite in sign, then so is true for the components, and that's going to push me in. So we can see what this is going to do. Oops, let's see. Woo! It's going to take a little box, and it's going to push it in along 1 minus 1 and push it out along 1, 1. And that's telling us the fact that 1, 1 is the eigenvector corresponding to e to the t, which grows as t goes to infinity, and 1 minus 1 is the eigenvector corresponding to e to the minus t. Again, going through it kind of quickly, hoping that that's kind of review. Okay, and one thing you notice, if you look carefully here, these boxes, I'm flowing whole boxes at a time for a reason. It's a little hard to be sure, but what's happening is they're distorting, but they're not actually increasing or decreasing in area. They get very, very distorted if they go anywhere near the origin. They always get somewhat distorted, but I claim they actually stay constant in area. And we'll talk about that in a minute. Okay, so the flow lines trace out hyperbolas because that's what cosh and sinh do. If you look at, for example, the flow of 1, 0, that's exactly what the first column of this matrix represents. Cosh t sinh t is exactly a good way to trace out a hyperbola. That's a good thing to know. And it's just the hyperbola that is tracing out here. Let me just go ahead and do integral curves. Oh, come on. There we go. So if I go here, it's not auto-starting for some reason. Okay. They're hyperbolas except when I start on one of the axes, in which case it's degenerate. It's one of the asymptotes of the hyperbola. Okay. So very classic system of differential equations, one that you should all definitely look at in doing differential equations. Very simple matrix, very simple behavior, and you get attraction along a certain line, repulsion along another line, and in between it's hyperbolas. I'll also mention that these matrices are very cool in relativity. These are exactly the Lorentz transformations in relativity, at least if you just restrict to one space and one time dimension. Okay, now let me look at an even better example in some ways. 0 minus 1, 1, 0. Okay, so let me put that into the vector field analyzer. Minus 1, or in other words, the vector field is minus yx. Whoa! You can see what happens there. We are exactly equipped as a species to see what's going on with that. And I'll start an integral curve. Voila, it's supposed to be a circle. So somehow sines and cosines have to come out of this. And it's a classic example of how Euler's formula makes that make sense. I diagonalize. It turns out here, good exercise again, pause if you want to do it, that the eigenvalues are plus or minus I. The matrix of eigenvectors is 1 minus I, 1I. Here's the matrix, the inverse matrix. And if you put this all together, you're going to get e to the ITs, e to the minus ITs. You put it all together, you get exactly cosine t minus sine t, cosine t. This is the rotation matrix. This is the matrix that takes any point in the plane and rotates it by t radians. And that's exactly what this is doing. Takes this point here and go. Start rotating by 0 radians, and then eventually pi over 2, and then pi, and keep going and going and going, rotating by more and more and more. And in particular, the trajectory of any point, for example, 1, 0, is going to be cosine t comma sine t. That's exactly, very early on in learning trigonometry, we understand that that traces out the unit circle. Okay. Here, it's very clear, the statement that if I look at a box, for example, that does preserve its area. It really preserves its entire geometry. These transformations that are induced by the flow, the transformations of the plane, are isometries. They are just rotations. They preserve all geometry, in particular area. But in the other case, it wasn't isometries. They were visibly distorted. But the one thing secretly that was being preserved was the area of these boxes. Very important, this idea of an area preserving flow. It shows up a lot in more advanced mathematics. Okay, so that's the thing I wanted to emphasize. Why was that true in these two examples? It's because the determinant of all the flow stages is equal to 1. The A of t matrix, let's go back to the cosh sinh example. Cosh squared minus sinh squared, that's an identity. That's equal to 1. Okay? And of course, cosine squared plus sine squared is equal to 1. In both cases, all these A of t matrices, which tell us the transformation from the time 0 case, let's go back to here, like the time, let's say that's time 0, there's time 1, you've done a transformation of the plane, it's an area-preserving transformation because the determinant of a 2 by 2 matrix measures the distortion in area. Okay, and so it's really a nice calculation that the determinant, let me go here, yeah, the determinant of these is equal to 1. It turns out there's an even deeper reason for that. Remember, in the differential equations perspective, what was really crucial was the matrix B, or LNA. It was the infinitesimal motion. Turns out that's really coming from the fact that the trace of that matrix is 0. Trace of this matrix, clearly 0. Remember, the trace is just the sum of the diagonal entries. Here, again, the sum of the diagonal entries is 0. There's a very cool fact, which I've pretty much given you enough hints as to how to prove, but I'm not going to worry about it right now, that the determinant of an exponential is the exponential of a trace. And even if you have a factor of t here, it certainly still works. So if this trace is equal to 0, then the determinant of all the exponentials is going to be equal to 1, because that's e to the 0. And so that's a very deep reason why those two examples have this very nice property of preserving area. It's also equivalent to having the product of the eigenvalues of all those stages of the flow equal to 1. And we've talked about that. The product of the eigenvalues being equal to 1 was the necessary condition for identifying our Fibonacci stuff, the twisted Fibonacci with sines and cosines. Okay, so let me bump it up even another notch. I know it's getting a little bit more advanced here, but that's kind of how I wanted to finish it up. Let's look at what happens if we don't twist, and if we don't have the product of the eigenvalues equal to 1, and therefore an ability to identify with sine and cosine. So in general, we've got alpha and beta to the t, as that's our a of t here. I should have a t. I'm going to write those as exponentials, e to the t ln alpha, e to the t ln beta. Okay. Now, in terms of sequences, what does this mean? It means that a very simple way to say it is that one eigenvalue to the n will definitely satisfy the recursion relation. Okay. That's just what happens if I take this guy and I don't bother to change it by p and p inverse. I just leave it as is. That's just alpha to the t, and there's just beta to the t. Okay, and so a nice way to think about, fairly low-tech way to think about this process, is we're finding two geometric sequences that satisfy the recursion relation. And that'll only work if the common ratio of those geometric sequences is very, very special. They have to exactly be the eigenvalues of the matrix, the solutions of the characteristic equation. Okay, that's something that even if you're kind of like, well, I'm not sure about this matrix stuff, you can check on your own. If alpha and beta are given by the solutions of the equation we had a couple videos ago, the quadratic involving p and q, you can directly check that alpha to the n plus 1 is p alpha to the n minus q alpha to the n minus 1. Similarly for beta. Okay, but and then what we've been doing is we've been seeing that we take combinations of alpha to the n and beta to the n. We subtract or we add and then we scale. And the thing is, if q is not equal to 1, those aren't reciprocals of each other. And we've seen that those combinations, like pluses and minuses, whatever, they won't just be sines and cosines. And even if we're clever and put in complex arguments, it's just not going to happen. But here's what we really get in the very general case. You're going to have sines and cosines combined with an exponential. And it's all about the twisting. Okay, so we're going to see, what we're going to do is we're going to twist it, and then we're going to twist it back. Okay, so let's let k be the square root of q, and if q is not a positive number, we have to make some fairly arbitrary choice of complex root. For example, long time ago, we really took the square root of minus 1 and used I instead of minus I for no incredibly good reason. Okay, so here's what we're going to do. We're going to take x sub n, which is alpha to the n, and y sub n, which is beta to the n, these sequences that do satisfy the recursion, and we're going to twist them. We'll divide them by k to the n, so that's just another way to write that. Divide this by k to the n, that's another way to write that. Okay, we know that that satisfies the twisted recurrence, okay, where the p gets divided by k, because we're twisting by a 1 over k factor here. And then this guy was a q, and the twisting divides it by a k squared, but k squared is q, and so that becomes 1. Okay, and so that's exactly what I've been talking about before, is to get in the sine and cosine framework, we have to twist it so that this guy, there's a 1 secretly in here, a minus 1 times a sub n minus 1. Okay, note that in this case, beta over k is just the reciprocal of alpha over k. So I've kind of split the difference. The k kind of splits the difference in kind of the geometric mean sense between the alpha and the beta. It is, I guess it really is the geometric mean, isn't it? Hey, yeah, it's the square root of alpha beta. So k is the geometric mean of the two eigenvalues. That's a really good thing to say that I should have written down. Okay, so now what's going to happen? So let's take alpha over k to the n plus beta over k to the n over 2. That should end up being the cosine of something. And indeed it is. It's 1/2 times e to the n times ln of alpha over k plus e to the minus n ln of alpha over k. Oh, and because I'm using this fact, I want to write everything in terms of the alpha. Okay. And so I've successfully written it as a half of two exponentials, and those are negatives of each other. That can be thought of as the cosine as long as you set L to be 1 over I, or in other words, minus I times ln alpha over k. Same thing as minus I times ln k over beta, again, because k is the geometric mean of alpha and beta. Okay, so if you let v sub n, if you go back to v sub n, what you're supposed to do, the v sub n sequence for the original problem, where I didn't twist it, was just supposed to be this eigenvalue to the n plus this eigenvalue to the n. That gives you a nice integer sequence. And what is that? It's all this stuff, but times k to the n, and then times a 2. Okay, so the v sub n sequence, I started with that one because it's just a little prettier, is always going to be 2 times an exponential with the ln k here, and now that might be a complex exponential, okay, might be do funky stuff, times a cosine. So this is a completely general thing for any Lucas sequence, if you care, that you can express it in this way, where L is this funky, complex ln of a twisted version of one of the eigenvalues. And similarly, a little more complicated is I'm going to create something that should look like a sine. I'm going to take something to the n minus its reciprocal to the n all over 2i, rewrite that in terms of exponentials. That's going to be sine nl, where L is the same exact number. And then I'm just going to recover, I'm going to undo the twisting to recover u sub n. The standard sequence that I'm always supposed to create, that's the sequence that starts from 0 and 1, from alpha and beta. It's going to be able to be written as a scale and a twist and a sine. So this is the general version of what we were doing with the Fibonacci. In our case, k was equal to I, and, well, yeah, no, in our case, k was equal to 1, and so we didn't need the exponential factor. Oh, no, I'm sorry. In the original case with Fibonacci, k was minus 1, and that's why we needed the I to the n factor, of course. So we get the scaling, the twisting, and the sines and cosines. And finally, we're done.